So I guess this is homework 5, and these are some exercises to sort of get some practice with the notion of pack learning or statistical learning in general. And yeah, so question 1 was just a very concrete example of a hypothesis class where a hypothesis class is just, I guess I should say this is a classification problem, so the labels are just 0 and 1, and the domain set was R2, the plane, and the hypothesis class was this set of functions, which are the indicator function for closed disks, or the set of points for the set of vectors in R2 where the magnitude is less or equal to R for R bigger or equal to 0. So these are like, we're just trying to classify points or like into falling within a certain disk. And then we wanted to show that under the assumption of realizability, this class is pack learnable with a certain sample complexity, which I guess we discussed in the last lecture, was saying that this is a one-dimensional class, both in terms of the parametrization, but also in that case it matches up with the VC dimension being 1. So
and also with the, what you could say, the topological dimensionality, which could be different from the number of parameters.
Sure. I guess if it's a degenerate parametrization. Yes. Yeah, I was going to ask Ohad, could you walk us through your solution?
Yeah. So, okay. So, we set to define a learning algorithm. Okay, I focused on the case of a classifier, so y is 0 and 1, and then given a set of m points, I look at all the points with y equals to 1, and then I take out to be the maximal radius out of all of these positive points.
This max of the norm of xi for which yi is equal to 1.
Yeah, and then I reset to bound the error of this algorithm depending on m. And here this algorithm has no false negatives. Sorry, it has no false positives, but no false negatives, or the other direction. I'm not sure. The confusing terminology.
No
Right,
false. Has no false positives, I think.
Yeah, because it's I guess if we assume realizability, so let's say this green circle is a true hypothesis, and then we see a number of samples here, and we take the radius of the maximal one. not very good at drawing circles, then it's always going to be like within the true hypothesis. So we won't have any false positives, but it might have some false negatives in the kind of space in between. Right?
Yeah. Okay, so yeah, we take a general distribution D, and because it's realizable, we can describe it by a true radius, which we call R star. And we know that all the points xi that are in this true set have radius at most R star. So if we take the maximum of all of them, we get that R is less than or equal to R star. And then the loss, the probability of making a wrong prediction is the probability for random X from the distribution that the indicator of it on BR, the ball of radius R, is different than the indicator of BR star.
I guess maybe you could say loss of H sub R.
Yeah, where HR is the indicator of BR. That's our prediction.
I think I've had to write this maybe indicator of like normal X less or equal to R star.
Yes, so that's the true value, and the guessed value is the same with R instead of R star. And then because R is less than or equal to R star, that's exactly the measure of the difference between the two balls of BR star minus BR.
I guess
Okay,
BR is a closed ball.
Yes. And this is a function that's defined on all R from 0 to R star. It has some interesting properties. It's not necessarily continuous because the measure might have some singletons, but I did prove some properties of it.
That's it.
Yeah.
Not necessarily continuous. Maybe we could say, because I think this was one thing that a lot of people basically assumed it was continuous, but maybe we could say, why not?
Yeah. I also take the domain to only be up to R star because we know that our guessed values satisfies this, and the other interval is kind of weird. Yes, so it's not necessarily continuous, but it is monotonically decreasing, and the error goes to 0 as R approaches R star. And it's also continuous, and it's also right continuous. And we can prove this by noting that the family of closed balls BR is itself right continuous, because if we approach a certain radius from the right, then the intersection of all of these closed balls is exactly the small ball in the limit. Yeah, and from there, Okay, so we have a general parameter epsilon greater than 0, and
Yeah,
and
so
we want
maybe we could say what right continuous means exactly, because
yes. So the function being right continuous means that for each point x in the domain, the limit of f of x plus epsilon approaches f of x as epsilon approaches 0 from the right. That is, we only consider right limits in the function graph.
so it's like if you take a sequence of points from the right, then it has the right limit. Or maybe like an example of like a kind of function like this. It's something that's not continuous, but it's like, I guess it's right continuous. There's a question in the chat. If it's piecewise continuous, well, I mean, piecewise continuous generally means it's continuous.
Yeah,
right. It's like composed of continuous. You could get it as a like several restricted functions with non-overlapping domains that where these domains add up to sum up to the entire R. Well, I'm asking this just as a like trivium. It's not like super important.
I think in spirit, yes, you can probably get some more complicated things. Like it's not necessarily like a finite, doesn't break into finite segments, but I think that's a fine way to think about it in the like first approximation.
yeah, and I think in general, the number of points of discontinuity can be infinite. I'm not sure if it's always countable, but it can be quite weird. Okay, so yeah, we have our function, and now for a given parameter epsilon greater than 0, we want to bound the probability. We wanted to bound the probability that the loss is greater than epsilon. Yeah, this is just substituting the definition of PAC learning, but here the ideal loss is 0 because there is some perfect hypothesis. Yeah, and technically, I think that we want to bound the probability that the loss is strictly greater than epsilon, because the definition of learning gives us a lower bound on the less than or equal to, and then we change the direction. Okay, so now if f is the function we defined earlier, that is right continuous and represents the loss, then I defined R0 to be the minimal element R, that such that f of R is less than or equal to epsilon. Yeah, so using the properties of f, we can show, first of all, that this set is closed, and thus R0 is in that set, so that f of R0 is less than or equal to epsilon. And we also get that the set f of r is greater than epsilon is exactly the set of points less than r0. Mm,
F of r is greater than epsilon if and only if r is less than r0. Is this?
Yeah. Yes. So that's exactly the way to formalize the point that R0 is the cutoff point. We we'll say that we're in a bad set if our radius is less than or equal to R0. And then the probability that S is a bad set, that is alpha S is greater than or equal to epsilon, is equal to the probability that R of alpha S, the radius of the hypothesis, is less than R0.
So this is you're saying this is bounded up by the probability that yeah, I think
Yeah, that the radius of alpha S is strictly less than R0. And now this event means that for all positive points, that is points where points in the set where yi equals 1, then xi is smaller than r0 in magnitude.
so okay. And this happens if and only if it's for I such that yi is equal to 1. We have norm of xi less than r0. That's right.
Yeah, and the wait, so for each point xi, for each point xy from the distribution, the probability of that to happen is exactly the probability that either yi is 0 or that y is 1 and the xi is small. The probability of this to happen is bounded by 1 minus f of r0. Because that's exactly the complement of the other event where we defined. Okay, and since r0 is right, yeah, and f of r0 is less than or equal to epsilon due to what we said above. So we can bound the probability of each specific point by 1 minus epsilon.
Wait, so is this is an upper bound on the, because if f of r is less or equal to epsilon, this is bigger or equal to 1 minus epsilon.
Yeah, wait, let me.
Did I read?
Oh, maybe I had. Okay. Okay, so in the definition here of R0, let me think. Okay, yeah, it gets kind of confusing. Okay, I'm not sure how do the directions work out. I do know that in the case that f is continuous, then it all works out because f of r0 is exactly epsilon.
Mhm.
I think. Yeah, so yeah, it's I'm actually not totally sure how to settle this.
Seemed like the right kind of thing, but maybe I wrote one of the inequalities the wrong way. So let's see the so we have this correct circle R star, and then we have our distribution D. I guess dx, which is just a distribution on the plane. And then we were trying to pick R0. So then the loss.
Yeah, so they continue assuming that f is continuous.
Well, it would be nice to figure this out because this argument should work in general with the because yeah, as I said, f is not necessarily continuous.
So I think I'm not sure if the R0 has the same function as something in my proof, but what I was trying to do is I was finding the largest R0 so that the closed interval between R0 and R star contains at least or more than epsilon of the mass of D.
The closed interval. For some reason, I feel like it's it'd be like a half open interval, no? Because we're like sort of looking at the.
So I was first finding the closed interval to define R0. And then the thing about the sample depended on a half closed interval inside of this interval.
I see, yeah.
But in order to define the R0, I used closed interval because it kind of worked with having an arbitrary measure that does not need to be continuous, I think.
Right. Okay. So let's see.
And the definition was also a bit tricky because it was the idea is that you can define R0 because you can take intersection of closed intervals and they remain closed. And that made the proof work, I think.
Right, which was the idea that I had mentioned too, that these closed paths you can get.
It's probably a different language for the same idea as the right continuity. But basically, I used closed interval to define R0, even though the interval we had to consider for the loss was half closed, like you said.
Right.
And so basically, I think I could prove that the mass in the interval. Yeah, I would need to look at what I wrote.
Okay, so maybe
Yes,
maybe
that
for
if you have a half open interval between some R and R star,
yeah.
which with R larger than R0, then this one will be smaller than epsilon. If you take for R0 the largest, which is not smaller than epsilon.
Let's see.
Can you repeat your definition of R0, please?
Yes, so I take as R0 the largest number, so that the closed interval between R0 and R star contains greater or equal epsilon as mass of D.
Or is it there? It's like, yeah, okay. So it's a supreme of R such that the measure of oh yeah, okay. Yeah. The measure of the R star ball minus the interior of this one is
Yes,
I guess
exactly.
lesser equals epsilon.
Is larger or equal.
Larger equals epsilon. Yeah, it's
I think then you still end up with a half open, the way you've written it. If a ball is closed and you subtract the closed ball, then you get a half.
No, you subtract the interior.
yeah,
He
so
subtracted the interior.
Oh, that's what that.
Oh yeah, this means interior.
And how do you know R0 exists? Like
sorry?
Supremum, sorry. Yeah.
Yes.
Yeah, but then I think you have a similar thing where if you take the loss over the R0, then that one should be.
Yes.
Uh,
And once you have this R0, you see that if you have R which is larger, and if the half open interval between this larger R and R star was larger than epsilon, basically you could replace R0 by something larger, so the supremum would be larger.
Right. Okay, so yeah, I think with this, yeah, we do get that. So basically, we're trying to get a bound on this probability. It's like 1 minus epsilon, and then for the m points, it's like 1 minus epsilon to the m.
Yeah, and then we bound this by e to the minus m epsilon, like in the notes, and this shows that whenever m is large enough, then this probability is bounded by delta.
And so if m is bigger, equal to like log, like 1 over delta over epsilon, and the ceiling should be enough to imply that the This is less or equal to delta.
Yeah. I think that another possible way to handle the non-continuous case is that first of all, we prove this inequality for all continuous distributions D, and then given a non-continuous distribution, we construct a series of continuous distributions Dn that converge to it, and then the error of D is the limit of the errors of Dn, which is also bounded. But I'm not sure if this works.
Yeah, or something along those lines would also work. Yeah, I guess the maybe just the
There's,
important thing.
There's something so intuitive about the basic argument here that is so hard to put into good mathematical language. I
Right,
also really struggled because you can see, okay, there's going to be an interval in R in radiuses, and in order for the expected error to be a certain amount, all of the samples have to not fall into a region with the same epsilon probability mass. But it's very hard to state that succinctly. Very interesting.
It is. It is a little tricky when if you assume it's like you have a probability density function or something, then I think that's what a lot of people did. You just write down an integral and then you just take a cutoff point. But then of course you can have like a delta distribution somewhere, sort of a spike in the distribution, which makes it not work. So one has to be a bit careful. But I think this this method with looking at the mass of the closed ball minus the open ball, I think that actually works well. But yeah, it's a little tricky to do this precisely. And I think what Ohad was saying with the continuity should also, that one-sided continuity should also work. It's just a little confusing to get the definitions right to get the right inequality. Yeah, but yeah, thanks for Ohad and Jean-Marie for jumping in and putting it together. Okay, so maybe we can move on to question 2. Actually, I guess both of these questions were in like full precision, were quite a bit harder than I originally intended, especially for question 2. I think someone asked if we had any assumptions on X. I said we probably don't need them, but as I thought about it a bit more, and actually Felix pointed out that things get quite a bit subtle in the word generality. So I think maybe we can, for this discussion, assume X is finite and kind of get through the high-level ideas, and then maybe we can come back to see what we need to do if we wanted to say something more general. So for now, let's assume and maybe Adi, if you're open, could you walk us through your solution?
Sure. Even though I'm not sure why do we need the finiteness assumption?
Well, okay, maybe we can not assume it for now and see what happens.
Yeah. Okay. So so for the first part of the question, we wanted to show that for every distribution, I can find an algorithm which is better than any other learning algorithm, well, better means that its loss on any specific sample is minimal. In this case, and oh, okay, I think I see why we need x to be finite. So I'm going to define the algorithm to be the algorithm that always returns an optimal hypothesis, no matter which sample we got. And since we took the optimal hypothesis, it's going to be to always have minimal loss.
Right, so we define
If
alpha of S for any S to be
argmin over the over
the hypothesis.
yeah.
Right, so here this argument might not exist if so if you assume X is finite, then the hypothesis class is also finite, so this argument always exists. And then if X is not finite, then depending on whether or not H is compact, this might not exist. But anyway, so assuming finite, or at least assuming H is finite, we can do this. And then maybe one thing worth saying here is that if you allow H to be anything, like if it's the class of all functions, then this argument is actually exactly the Bayes optimal predictor that we saw in the entry questions, because that's the one whose loss is less or equal than anything else. Okay, so but yeah, without going into that, if for any finite H, we can always just something add in the argument.
And as for the second part of the question, so we wanted to show that if we have at least two hypotheses in our hypothesis class, then for every learning algorithm, we can find a distribution for which it is not optimal. That means there's a better algorithm B with respect to this distribution. So what I do is I suppose that A, for example, returns H1 on the empty string, just for like a particular. Oh,
yes, assume.
H1 is A of alpha of gamma. Yeah. And so I pick some, because H1 and H2 are different hypothesis classes, I pick some element in X on which they differ. And I choose my distribution to be the distribution which is which puts all the probability on x comma h2 of x. And now clearly beta is better than alpha on the empty string, and that shows the result.
So in this case, the loss of alpha on the empty string is equal to 1, which is bigger than the 0, which is the loss of beta on the right. Right.
This somehow feels like a really extreme, like edge case.
It feels like cheating.
Oh man, well done.
Right, but it works. I mean, it's the kind of like minimal counterexample you can have. It's kind of interesting to see if, like, let's say we require alpha to be worse than beta on like a certain sample size not 0, then you need to work a little bit harder, because if you want to assume that that sample has positive probability, then we need to make sure that whatever beta returns, we can still define a distribution just as like a small probability on that sample when alpha gets the wrong thing. But yeah, for this, interesting to do is to just consider the empty sample, and then it's very easy to construct a counterexample where beta does exactly the right thing. Yeah, thanks, Adi.
And it is also, you can like draw out the reasoning for what this points to, like what this is pointing to in terms of the overall result, because you can basically say, okay, so we're in some real world situation, we have some hypothesis that gives a certain classification for a certain sample. We can always consider a distribution in which the probability of that particular sample is really low, and where in fact the right answer is something different. So that's a sort of legit situation that this points to, that you're not going to find some learning algorithm that's better across all distributions and samples, basically.
Yeah, exactly. Yeah, that's a good way to put it. And it sort of highlights also this notion of pack learning we had. It was a statement that was something about something being true for every distribution in the definition of pack learning. So in that sense, it's sort of like it's kind of almost like an adversarial statement where you're saying like there's no distribution that can cheat us, and as we see that, for any specific thing, we can always make some very kind of sneaky distributions that's like trying to do exactly the opposite of what the algorithm is predicting. So in that way, it's pack learning is a fairly strong requirement, because
yeah, like you could define definitely always correct learning, DAC learning, by this, right? This would be the definition for definitely always correct. And then you can prove, okay, it's just, you're never going to find, nothing is DAC learnable. Nothing with more than one hypothesis is DAC learnable. But if your hypothesis class only has one hypothesis, then it's DAC learnable.
Yes. Yeah.
So is the idea of question 2 that doing the limits as the sample size increases is like important for a useful definition?
Yeah, I mean that's one kind of takeaway that yeah, really back learning is only in the limit of the sample size. And yeah, I guess I mean maybe the thing to emphasize is that the freedom to choose the distribution, like a statement about every distribution is quite strong. Like it's sort of a, as I mentioned, it has this almost adversarial nature where the distribution could be really working against you. And yeah, so the difference between part 1 and part 2 highlights how, assuming a fixed distribution looks very different than allowing the distribution to be arbitrary. Yeah, and then there's a kind of interesting thing that Felix pointed out that I didn't think about before, is just that if you don't have this finiteness assumption, this whole thing becomes quite a bit more complicated to do rigorously, which I think it gets a bit technical, so I don't know if it's worth going into.
But it still is correct in the infinite case.
I mean,
I don't think so.
I think if we if you take, for example, h to be all functions, then and let's say we have a d which is a distribution over x plus y. So I was only thinking about this today, so I might say something wrong. I don't know if Felix is here. He's good at catching this stuff, so you can correct me if I say something wrong. But so given this, we have a probability distribution on x, which is the projection of this, and then we can talk about first of all, I guess to say this is probably already not quite right, because we probably want to say that we restrict to like maybe only measurable functions, which if x is like the real numbers, for example, then this entire function space would include some non-measurable functions for which the loss is not, it doesn't even make sense. So, but if it's measurable, then I think that implies that the loss is well defined.
Are we in the realizable case or not? Because I think in the non-realizable case, it's just wrong.
The statement, like the statement is not true.
Yes, because in the non-realizable case, you can just have your space be something like an interval minus a point, your space of hypothesis.
Right.
And then you can just have the right hypothesis be this point which is missing. And then
Yes.
there is no better algorithm. So if we can make a concrete example, like for example, you have x be an interval, and you have your hypothesis space, which gives 1 to the points larger than epsilon, strictly greater than 0 for the different epsilons. And because you cannot take epsilon is equal to 0, you can choose d, which always gives 1 to all the points. And you can always find a better hypothesis by going closer to, by taking smaller epsilon.
Right, so if age is not compact, then we don't generally have argmin at all. as Jean-Marie pointed out. So I guess I was trying to say, like, what does even compact mean here? Because I guess we have this space of functions from x to y. And then I guess I was saying that we probably want to restrict to measurable functions. And then we want to put some topology on it for which, yes, an interesting question is like, what topology on y to the x makes, so we want, I guess we would want the this last function to be continuous.
But that might depend on D, right? So maybe there isn't a single topology.
Yeah, but I mean well, I guess. So we'd probably want to ask, well, okay. I mean, there's a few different ways to go about it. You can either fix D first, which means that it kind of turns X itself into a probability space, which comes with a sigma algebra of measurable sets, and then you can talk about the measurable functions with respect to that sigma algebra. Or you can say, like, fix X as a fix a sigma algebra on X, and then pick a D which is measurable with respect to or a measure which is I guess a measure with respect to that sigma algebra, and then ask for this to be continuous for all D.
So it is more usual to derive a sigma algebra from a topology than the other direction. I
Right.
don't know.
I mean, that's
It's more often done. So
I mean, we
maybe
don't.
we should start
Yeah,
with a topology on X.
well, we don't necessarily need a topology on X, right? We can just take it to be just a measure space.
Yes,
what we
but
need
then
is,
you will not have a topology on H either, probably. Or you.
well, I think
Oh, yeah.
I think you can put a topology on the function space, and then that's the question of what topology to put on the function space. It makes this continuous and maybe makes y to the x compact. So that's a question of, like, is there such a topology? Because if there is one, then then you can say that there is an argument. And I think there's this notion of convergence with respect to a measure, which induces a topology and maybe has these properties. But as I said, I only started thinking about this today when Felix pointed out that this is kind of subtle.
But
I
this
don't know,
is
yeah.
this arises from taking the argument over hypotheses. I did a very naive thing, but I actually don't know why it's wrong. I just said, let's define for each x the hypothesis that chooses between y being 0, y being 1, according to which of those two have higher probability.
Right.
What
But
am
then,
yeah, what am I assuming there that I shouldn't be?
So
I mean, I think that's a good
what we
approach.
did,
Yeah.
but it's a different
good
understanding
approach.
of the problem. Sorry.
It is. I mean, it is basically saying that you construct a base optimal classifier. The issue is that, like, basically now we're talking about, like, does that actually exist? Because in the definition you're talking about a conditional probability of y given a certain x.
Yeah.
Which if x is finite, then that's fine. You can define that. but for kind of an arbitrary x, it might be
Right.
there's not like a very clear way of talking about that conditional probability. But as I said, this is getting pretty technical, so maybe I was not expecting people to go into this much detail. I just didn't realize how subtle it is in the full generality. But yeah, it's I thought it's worth mentioning that there's quite a bit of subtlety here if you don't assume things to be finite.
So basically, you can't pass from like a distribution on X to a probability density function without making assumptions about the
Right.
topological structure of X. Interesting. That makes sense, actually. Because yeah, you could get this situation like we had in the previous question, where this distribution D is non-continuous, basically, and then you wouldn't have a well-defined probability density function. So you can't just take conditional probabilities and stuff.
Yeah, exactly.
And
So yeah.
there was maybe another confusion, which is that there are two slightly different definitions of a learning algorithm. So sometimes it seems like you can only return an hypothesis of H, and sometimes it seems you can return an arbitrary function from X to Y.
Right. Yeah. I guess sometimes you just assume that the hypothesis class is every function, in which case you just get a return of a function, which is what I was saying here, that if we take every hypothesis included in the hypothesis class, and if this whole space is compact, then the hypothesis class itself is compact. And of course, if X is finite, then any subset of all the functions is also finite, so we can still take the argument over the hypothesis class as Adi mentioned. But yeah, in general, we have these two subtleties where we need to see that this space is compact itself, and also if the hypothesis class is not everything, then that subset that is the hypothesis class itself might not be compact. So there's definitely kind of two subtleties going on there, and neither of which is I intended people to get caught on, but yeah, I guess they're good to pay attention to if you don't have this finiteness as absolute. If someone knows measure theory well, I would be curious to if this is indeed the case, that the convergence with respect to measure gives us a topology which has these two properties. But yeah.
Or that you can basically, like, what do you need to assume about a measure in order to be able to compare the probability of 2 points? Like, I agree you can't just do that, but you should be able to say something. Yeah, something.
Right, but I mean, by comparing the probability of 2 points, you mean like whether you have a probability density function which allows you to do that?
Yes, but maybe you don't need to go as far as actually having a probability density function just in order to be able to compare 2 points. I agree you need to assume something, but if you have a measure on X, like, what do you need in order to be able to meaningfully say that there is like more density at like the point x1 in X than there is at the point x2 in X.
Yeah, I'm not sure I fully understand the point.
Basically, because then you
saying
can then you can define the Bayes optimal classifier
Right,
point-wise
yeah.
rather than as like an argument over the whole hypothesis space.
Right, yeah, so yeah, that is. It is a good question of like, in what generality can the Bayes optimal classifier be defined? Yeah, yeah, I'm actually not sure about the answer myself.
Because if you have an interval with a point missing, there are many cases where you can define the Bayes optimal classifier over such a hypothesis. You know, it's a hypothesis space, but you can still define the Bayes optimal classifier in that case. We have to make other assumptions.
Anyway, yeah, so we can maybe stop here. Are there any questions related or unrelated we can discuss for a few more minutes?
I have a little question about question 1.
Mhm.
So is it possible to make another strategy work to solve this question where we pick an hypothesis between the largest point giving 1 and the smallest point giving 0? Can that kind of strategy also work?
So say it again, what's the strategy? This is a...
So in Ohad's answer, basically he was taking as a hypothesis the largest point giving 1, basically the point most distant from the origin.
Right, yeah.
Can you work with an algorithm which has a different definition where you, for example, pick in some way an hypothesis between the largest point giving 1 and the smallest point giving 0? Or can you make that kind of thing work?
That's a good question. I feel like maybe because of having like the closed disks, if you have a distribution which is concentrated like right on the edge of the true radius, well, maybe that's still fine. Yeah, I'm not sure. So what sort of thing do you have in mind? Like we have, let's say we have the
So the first
negative
thing
points.
you could think of, if you were in a practical situation, you would, for example, take as the limit the average between the largest point giving 1 and the smallest point giving 0. Like you would take as radius the average of the radius of the largest radius giving 1 and the smallest radius giving 0. And in practice, I guess most people working would just take the average of the two. But if you try to make a proof with this idea, it doesn't work as well, I think, but I'm not sure.
So you take like the closest point here and then the closest point here, and take the sort of average radius between the two.
Yes.
Yeah, yeah, it seems like a reasonable thing to do in practice, and
But it seems like it
but-
doesn't work. I'm not quite sure, but
it doesn't work. And it
So-
doesn't work exactly because of this, like certain spiky distributions might make it fail. Is
yeah,
that,
it seems
Yeah.
that like you lose a factor of 2 or something in the formula, or you lose a little bit if you do this,
Mm.
which was a bit shocking to me, because at first it looks like a better idea.
right? Yeah, it's an interesting phenomenon. Yeah, my guess would be that it probably doesn't work because of the just because of the precise nature of like how we define the things to be closed balls. Like if you did open balls, then maybe probably the opposite kind of thing would work, where you take the smallest negative example, right? So somehow because of
Yes.
so if we had something which is a bit fuzzier, rather than like exactly closed or open, then like I can see why in practice it's not going to be a realizable class to have exactly the closed one. So because of the fuzziness, like some kind of noise, I could see how it's actually better to take the average between the two. So I would think it's just because the setup was kind of artificial, and that's a forced one to be better than the other. Which, yeah, I guess it happens with this sort of fairly artificial hypotheses that they favor a certain kind of thing that's you wouldn't expect in practice.
Thank you.
Oh, I have a question about this question as well. What if your density, what if your measure only produces points with y equals 0?
Right, so you only get negative examples. Yeah, so I guess in that case, you would, I guess, yeah, Ohad's algorithm, where is it? You would just return
Oh,
a radius 0. You just take the radius 0 classifier, and if the distribution only produces negative examples, then you always get 0 loss, basically. So it still works fine.
Yep.
It's just a little, yeah. Bit of a corner
Nice.
case for sure.
Nice. That's nice.
All right, maybe we could stop here, and good luck on the last homework. I think I tried to make this. I thought the questions were fun for this one. They're maybe a little harder than average so far, but hopefully.
Yeah, I'm really stuck with them so far. I haven't managed to.
Yeah,
to figure-
if you want, if you want, maybe you can ask for a hint in the Discord, and if you're really stuck. Let me stop the recording.